Hello, my name is Nick Agius with BC Bearing Engineers out of Edmonton, Alberta, and the purpose of this training video today is to give you an idea of what we do when we're testing fans, when we're actually testing the airflow on air-cooled heat exchangers. We're not going to touch on cooling towers today. We can do airflow testing on cooling towers, but we're just going to be touching on air-cooled heat exchangers, okay? What I want to do is just give you kind of a I'll show you the tools. We're going to show you the all the methods and the little tricks that we use to use these tools properly. And I think that when you see how difficult this is, you might actually want to hire a professional to come in and do your airflow testing. But I do encourage end users to be able to do this sort of testing on their own because it's so weather dependent. You can pay for us to come in from wherever in the world to test your fans, but you know that week we're there, if it's real windy and rainy or whatever, there's not much we can do but sit on our hands. So I think there is a need for some of these simple tools that you can buy and with this guideline, and that you can do some good airflow testing and get a good idea. You'll be able to trend where you're at with your fans. Before we get started, I just want to say that this test that we're doing, this airflow test, is quite an involved test, and it's sanctioned by the ASME PTC 30. Okay, and so that's the governance that we actually work on for our airflow testing. Now there are people out there that do airflow testing, and they do real quick airflow testing. They can test a whole bunch of fans in 45 minutes. And what they're doing is they're taking inlet temperatures, outlet temperatures, they're back calculating and extrapolating what the ACFM, the amount of air that's being moved through that fan. That is not what we're doing today. I don't condone that kind of airflow testing. What we want to do is we're fan people. We want to know what the airflow in the fan is doing, and we're going to show you a test. It takes an hour and a half, 2 hours to do it properly per fan, but this is the proper way to do it. I want to thank a few people to make this possible today. We're going to be going out to Shell Scotford Refinery and doing some airflow testing. I wanted to do this inside the classroom just so we'd have an idea of it's so loud out there, so this gives us an idea of the tools, what we're up against. You're going to see some footage from us being out in the field as well. And one of the people that I want to thank today is Mike Norgren from Hudson Products out of Texas. He's with me today. He's done a lot of airflow testing, and his experience is very worthwhile for us, for Shell. Also, Chris Tardy from Gates Rubber Company for the belt drives on the air coolers. Chris does a lot of work with us. He really understands the air coolers, so you'll see some footage of Chris out there, and thanks Chris for helping out in Gates Corporation. Real big thanks for Shell Scotford Refinery, an engineer named Mike Booten. If you can imagine how difficult it is, this is the first of its kind, this kind of training video. I mean, you can't find this anywhere else, so this is important. Mike actually had to get permits for us to bring this camera into the refinery, so you can imagine how difficult that was and how much red tape he had to go through. And we really appreciate what Mike Booten has done for us today. Now, just before we get started, there's a few things that I'd like to say. First of all, back in July 2006, I wrote a technical paper that was published worldwide in hydrocarbon processing, and I wrote a paper on management of air coolers. Okay, it's really meant to be a management of air coolers, and what it does is it can tell you some things about your air coolers that you're not aware of, to keep your tubes clean, to kind of make sure there's no holes in your box. Don't pitch these too high, this and that. There's some formulas in here. It's very useful, and if you want, at the end of this video, we're going to give you some emails or some websites that you can actually get this information for yourself. So that's actually a pretty handy tool if you're talking about air coolers and you want to have some your people and your millwrights and your engineers a little bit more understanding how air coolers work. There's not a lot of people that seem to understand them. The first thing that we want to get before we do any fan testing, the most important thing is a fan specification sheet. Okay, and that's important. It tells us whether it's an ID fan, an FD fan. It tells us the altitude, it tells us the inlet temperature that fan was rated for, it tells us the ACFM that fan is supposed to be pushing out, it gives us the static pressure of that fan, it's very important. It also tells us the fan itself, it tells us the speed of the fan, tells us the horsepower that's hooked up, it even will tell us the belt drive and the ratio and the pulley sizes, whether it's V-belt, whether it's timing belt, all that information is there. That's very important because you're sometimes dealing with fans that are from 1965 and a lot of changes could be made. without knowing. I mean, a change that wasn't on purpose. Somebody supplied the wrong pulley. All of a sudden your fan is not running the right speed. Somebody went and pitched these fans up into stall, you know, so it says it's supposed to be at 10 degrees and you find out in the records that it's actually at 20 degrees. It depends also on whose fan's in there. I mean, some fans, like the Chittum fan, you can get it up into 30 degrees without stalling it, and other fans at 18 and 20 degrees, we're going to be stalling those fans out. So I don't like to actually ask or tell people what the maximum pitch of a fan is, because that's the wrong way to look at it, because every fan manufacturer might say 22 degrees, but it also depends on the speed and the static pressure. So really what you want to do is be able to learn how to read a fan curve. So the first thing you want is a fan specification sheet. Now let me tell you a little bit about this fan we're testing today. It's a 9-foot fan. It is a Hudson fan, okay? It's out at the Shell refinery, and when I look at the sheet, if it's pitched to 10 degrees, it's going to be using about half of the 20 horsepower, okay? So then Mike has a decision. Mike is asking us to help him today because he wants to get more airflow and he wants to get it more efficiently. So what's the most efficient way to get more airflow out of a fan? There's two things. We either pitch it up or we speed it up. The most efficient fan is the one with the least amount of blades, running with the flattest pitch, running faster. But there's some downside to that. One is noise, the other one is vibration. So we've got to be careful. We've got to make sure that we're designing this within the scope of that fan manufacturer's limitations. Most every fan manufacturer will have a program on their website, or contact them or contact us and we can work with you. The common ones that we really run into out there, we run into the Hudson, the Kaventco, the Moore, the Chittum. These are some of the common ones that we run into out there, and all these people are very good to deal with, so you can learn an awful lot. So back to Mike's fan, he's only using half his horsepower, so I give him one option, and here I show him in these sheets where we can actually get 9% more air by pitching it up, but the curve starts to look ugly. He starts to move towards stall, okay? What's stall on a fan is when you pitch that fan blade to a point where it's actually not moving air. It's going to be using horsepower, but it's not moving air. And that's kind of a fine line. You don't know when you're in stall. You kind of move towards and stall and out of stall sort of thing. And that takes experience, okay? But the fan spec sheet and some knowledge and some help from people like ourselves or the fan manufacturers can be a real aid. The other option that I like to give to Mike, and he liked it, was let's speed that fan up. It wasn't a noise issue. It wasn't a vibration issue. We didn't run into any resonant frequencies. So what we did is we're going to propose to speed that fan up to we're going to change the pulleys, okay? We're only going to change the motor pulley, and that's kind of unique. As we make that motor pulley larger, we actually help the horsepower capacity of the belt. We lessen the bearing load on the motor, so these are some added benefits of speeding up, okay? So what we end up doing is we're going to give them 24% more air by speeding up, and we're actually going to pitch it back. So 9% by pitching up, getting in closer to stall, or speeding up, improving our belt drive, and getting 24%. I think that Mike made the right choice by wanting to speed it up. Also, having a fan specification sheet can tell you a lot about the fan itself, like I mentioned. Here's a drawing right off of the Hudson website, and what it does is it tells us what the blocked area of this fan is. On top of this fan, and I've kind of drawn some pictures here of what the fan is. This is looking at the bottom of a fan. Now this one happens to be an FD, a forced draft fan with a fan underneath the bank, okay? So this is the bottom and here's the side view. So what we've got is a shaft coming up, we've got a hub, and then we've got a seal disc. Now what the seal disc does, it sits on the center, and we've got the seal disc on the Hudson, we got a seal disc on a Moore. We don't have a seal disc on a Chittum, they just use a hub. So that blocked area is either the hub if it's a Chittum, or if it's a Moore and a Hudson and nobody's put the seal disc on there, which is bad because again the air is going to start to recycle back down here and we'll get negative readings in our fifth reading we're going to go into here in a second. So what we do is we take the free area of the fan, which what we want is the fan diameter minus the blocked area, which would be the hub or the seal disc, and that gives us this free area. So here's the free area here, and we want to take a series of readings and calculate what the average speed in feet per minute is, and then we multiply it by the free area, and that's how we get our ACFM. As simple as that. Now it's simple, but it takes a couple hours, and you're going to see all the readings that we've got to take to do it. But again, by having the spec sheet, I can get the information off of whoever's website. I can see what the blocked area is, and I'm already prepared to go and do a little bit of airflow testing. What I want to do is, so what we do is we talk about the fan spec sheet, just the blocked area, free area. The other things we look for here, and I've put some notes down just so we can follow along, is the louvers. Are the louvers open? When we're testing a fan, the louver's got to be open. The fan's got to be working maximum speed if it's a VFD, or if it's an auto variable, we want to have it to maximum pitch. We want that thing working as hard as we can, and we have to have full cooperation from the operations people. We want to make sure that they know we're coming, and that's the big thing. You come to a plant site, they don't know you're coming, and then you're tied up with permits for another half a day or whatever. It starts to get very expensive. If they know that what we're doing is we're wanting to test a fan and we want to actually run it open, we have the louvers open, that's important. Weather. Can't be raining, can't be snowing, can't be really windy. Okay, so probably anything over 20 kilometers an hour is not so good for testing fans. That's where it gets expensive. This is another reason why it's nice if you can do some fan testing yourself, because you can pick the days. We fly in from Houston or from Canada or from wherever to do airflow testing, and we're sitting there for a whole week where it's rainy and windy. That gets very expensive. The fin tubes have to be clean. Before you even call up and give us a PO to come and do some airflow testing, you got to make sure your fin tubes are clean. Okay, if they're not clean, your static pressure is going to be high, so you got to clean your fin tubes. That's important. Seal disc needs to be installed. We talked about that earlier. Fan pitch needs to be either at the spec sheet. On this one here, Mike said 10 degrees, or close. I mean, I don't mind you going from 10 degrees to 12 or 13, but don't take it from 10 up to 18 degrees and expect that fan to not be performing badly. Okay, so what we want to do is we want to make sure that the fan pitch is in spec or close to spec. We want to make sure the fan speed. Now, you can either use some kind of tachometer if you want, or just go to the motor. It's 1700 RPM, 1750, or it's 1200 RPM. You've got information right off of the spec sheet saying the 2 pulley sizes. All this information, you've got all this before you even reach plant site. So you should know. Now you just go up with your tape measure through the guard, and it's supposed to be a 30-inch. It looks like a 30-inch. You go over to the motor. It's supposed to be a 6-inch, and it is a 6-inch. It kind of verifies the fan speed. But I don't worry about fan speed a whole bunch. I do, but I don't get all freaked out if I don't have a tachometer, because it's so easy if you've got all this pre-information. Okay, you want to take temperature, the outside temperature before and after, because if there's been a big change or you start testing and then a bunch of wind comes in or whatever and it starts to affect your readings, you want to make sure you take all that data in before and after. And also a kilowatt reading. We want to be able to know we use a kilowatt meter. I'll show you here in a second. The nice thing about the kilowatt meter is that it shows us power factor, and it actually will show us the true kilowatt, the power being drawn out of that motor. And we need to have an electrician on standby. We don't take those readings ourselves, but this electrician is going to do that job for us. He wants to do it sometime during the test, halfway through the test or whatever, and that's adequate for what we're doing here. Okay, and a couple of tricks here, and I'll introduce you some tools as I go along here. Oh, one is the spreadsheet, sorry. What the spreadsheet is going to do for us, I have the spreadsheet's available through us, or you can build one yourself. What we're trying to do is we're going to take a series. Here's our anemometer underneath the fan. Okay, and we're going to come in 4 different directions, and you can see on this particular fan it's got a big I-beam here, so I'm trying to break it up in quadrants. If there was no I-beam in here or no obstruction, I'd probably just come in at 6 o'clock, 3 o'clock, 12 o'clock, and 9 o'clock, okay, just to make it easy. And so I'm going to come in from 4 different areas. I'm actually taking 60 readings here, and I'm taking 5 different readings, 3 different times, 16-second average readings. And what I'm doing, though, is I'm taking this free area and I'm breaking it up, and this is critical, I'm breaking it up into 5 equal bands, and not distances, equal area bands. So in this particular fan, when I put this all, the formula is, the spreadsheet works real well. I just put in the fan diameter, put in the seal disc. In this particular case, it was a 38-inch seal disc. It actually automatically gives me the dimensions. So in this one here, my first reading is going to be 2.4, then 7.6, then 13.5, then 20.4, and then 29.2. So that's what this spreadsheet's going to tell us, and then we can actually just put our readings right in here. Now, before I move into the tools, I just want to talk a little bit about you can get thrown off here. A lot of fans will have what they would, if it's a Hudson fan or if it's been modified, this is a very good idea. There's a seal disc. So what this is the inlet bell. I apologize. The inlet bell comes in here, it takes the air, and it kind of creates the air not coming around a right angle. So if the air is coming around and trying to get in through a right angle, it creates some turbulence at the tip here, and that impedes the flow of air by probably 2 or 3%. Okay, so this is an efficiency thing. You'll see it on this Hudson fan tomorrow when we're out there. So where is that first reading? If you got this is where the training comes in. You might think that my first reading I'd said was 2.4 from the edge. It's from the edge of the fan ring. Okay, that's very critical. So you got to kind of get down there. You come under here with your anemometer, and I'll show you how we tape that up in here in a second. But then let's look over on this side here. Here's a very common one. We call it an elliptical valve, elliptical inlet. So you see it comes down, and I've seen, this is mainly a stork fan that I've seen these on. Nice little thing. It acts like an inlet valve. So you can see it actually has a taper that comes down here. So again, see this little imaginary line? My first reading has to be on the edge of the fan. So that's kind of important on some of the things that we're talking about. Now I'm gonna grab some of the tools here, and I'll walk through it, and then we'll do a little bit of a conclusion, and you're going to see some footage from some of this out in the field as well, and I think it's going to make a little bit of sense. So the first thing that we want to do is this is the anemometer. This is a vane type anemometer, as you can see right here. It has an arrow on the end here, and you should be actually when the airflow is going up, we want to make sure that we're in this direction and follow the arrow with the airflow. So you can see what we've done here is I got real smart. I've already taped off all those little dimensions that I mentioned. I've got those dimensions already here. So when I'm coming back underneath that fan, I'm standing out there, I can see where the edge of the fan ring is. I can measure my feet per minute. It's I take 16-second readings, and we do this 3 different times at each one of these, each one of these locations. Now, one of the little tricks that I'm going to show you right here, and we call this a Charlie hook. This is Charlie Taylor's now retired from Hudson. He's taught me a lot over the years, and we call this the Charlie hook. So what happens is your arms get a little tired because you're holding this as it goes underneath the fan, and you're holding that, and sometimes it's cold. A lot of times it's cold, or you're holding it up in the air, or whatever you're doing. This little Charlie hook just allows you to get your arms a little bit of a break, because it's very important when you're taking those readings that you're not tipping this wind vane. You want to make sure that that's nice and steady. It's very important to hold that nice and steady. The Charlie hook helps really well. So again, these are the readings. It's a 2-person job. I'm up on a ladder sometimes, a scaffold. Somebody else is down below with this, and there's a communication back and forth. What we want to do is it's loud up there, so we want to yell, because I want the person holding on to this. It's really hard. So again, this is what the anemometer looks like. A lot of times, like I said, I come out to a job. It's not the job I thought it was. I do always carry my Palm Pilot, or Mike, he always carries his laptop with him, because it's a lot easier just to put the, when you find out that it wasn't a 12-foot fan, it's a 13-foot fan, or it's whatever, or it has a different seal disc or no seal disc or whatever. You got to make sure that you did take some rough measurements. Even when it's running, you'll take some rough measurements from underneath. The toughest thing, and this is something that's very, very critical. There are 2 readings, okay? And if the day I can find an anemometer company that is actually going to give us negative and positive readings, you wouldn't have to worry about what I'm going to say. And you'll see it on this video, is that it is so hard to tell whether you've got a positive or a negative reading. Now this fan we're testing today, it's actually got good tip clearance. So if you've got a big gap in here, what happens is the air is coming up, it pressurizes the box. Here's everything, you're trying to cool the bundle up here. This will actually escape air. If that tip clearance is probably, you know, should be on a 9-foot fan, it's probably going to be, it should be a 1/4 to 5/8 of an inch, I think is what it is. Again, that's in that fan paper that I have. If it's an inch or if it's an inch and a half, all this air is going to come back down. So that first reading is actually, you know, it's hard to see it with a ribbon, okay, but it's bouncing around there. So you take a look, and that very first reading, you push it in. So you take your anemometer, and you actually are you're bringing it under the fan. Here's the fan ring. You come underneath, and you're actually looking at that vein. And if that vein stops or jerks around or whatever, you know that that's a negative reading. And what you can do is you jockey it in position. Okay, so there's the position where your tape is. So that first reading is very important because quite often that can be negative. The other one that's just as critical is the 5th reading, because here's where we're losing airflow here. This is where the tip speed's really high. This is where the tip speed's real low. Tip speed, the speed of the fan in feet per minute is a lot lower back here. So if we don't have this seal disc, or it's the wrong size, or there's maybe the tubes are all blocked and we've got a lot of pressure that we're developing up, you're paying for the air to go up and cool, and what's doing is it's coming back down and it's being recirculated. So this 5th reading, again, when you come in here and you're taking your 5th reading, what I like to do, you're taking that 5th reading, you got your partner down below. It's really hard for me to sit up here in a ladder and see where that thing is at. So when I go past the edge of the fan, you know, fan ring, to that point, I'll go a little bit further, and I've got my partner down below just looking at that vein. So before I get set up to actually take the readings and put my Charlie hook on here, what I want to do is I want to make sure that that's actually running the direction that I want. Okay, and again, if it starts to jerk around or go backwards or whatever, your partner looks up there and says, yep, it's going backwards, it's going to be a negative reading. And that's very important because you don't want to, you know, we've got to be careful to take the right data. If we sit there and call these negative readings positive, we're cheating ourselves because we have a fan that's unhealthy, we're calling it healthy. This is what we're investigating. We're trying to figure out what's going on here. I talked about the kilowatt meter before, so again, this is the kilowatt meter. You give that to an electrician, you make sure that you have that, you know, that all pre-planned ahead of time. This here is this happens to be a Hudson tool. It's an Exacta pitch, so that's a digital level that will read the pitch of the fan blades. Now, I don't worry about fan blades a whole bunch pitch because again, you know, it's hard to get the permits and the confined space and everything else. I'm going to have to believe what the customer says from the last information. Now the big trick here is to make sure that you've actually got the pitch reading taken on the right area of the fan blade. Okay, so on a Hudson blade, it's over here maybe 1 to 3 inches in from the end. That's where you're taking your reading. Now, on the Chittum, most of the Chittums have rivets, so you're going to be taking the reading back here. Now I happen to have a Moore fan blade here too, and on the Moore, you're going to be taking it back on the block. So this is what the Moore blade looks like. There's going to be an actual block back at the edge of the unit. Okay, sorry, at the hub of the unit. We're going to be taking the pitch reading here. So we got to make sure, you know, this is a good tool to make sure all the pitches are where they should be, and also to teach your customer, teach your people where to take that reading. I have a good customer out at Irving Oil, Lance Henry, has put a technical paper together. They have so many different fans. It's a big refinery. They have so many different fans that they get kind of, you know, it's hard to look up and find out which each one is where you're supposed to take the reading. So if you wanted a copy of that technical paper, we can get that to you as well, or contact your exchanger company, or contact us or your fan provider or whatever. One other tool that we have here, okay, and I haven't talked anything about this, so I've talked about the anemometer readings. This is a manometer, okay, and this is where we take the static pressure of the fan. This is a very important reading. This actually tells the health of the fan a lot, and it'll tell it'll also give us the efficiency of the fan. What we do is we drill the holes, and you'll see this today when we do the video. It's nice if people pre-drill those holes because then we're all ready to go. But we need to just pre-drill a little hole here so that we can put our little probe up and we can take the static reading. What we're trying to do is we're reading the static reading up in this box area of the fan. Okay, so if the tubes are all blocked, that reading is going to be high. If it's moving lots of air, it's going to be high. If it's not moving air, it'll be low. If there's a bunch of holes in the fan box, I mean, we want to make sure that those are repaired because that's going to lower the static efficiency. So 1, 2, 3, 4, this is a fairly quick reading. Usually what I do is I'll work with the anemometer first, and then I'll take these readings afterwards. Again, the electrician's taking the kilowatt reading, and then what we do is we'll insert all that information back into our spreadsheet, and it's going to calculate the health of our fan. That's our report. We can actually tell you what the fan is moving for airflow. Now, it's kind of important too, is another thing, is when you're looking at a fan, what I like to do is I like to do an inspection. You want to just make some observations, the health of the fan. You know, it says it's got a 30 horsepower, 1750 RPM motor. Go and take a look at that motor tag. Take a look, does it have a efficiency tag on there? Is it a 93% efficient, or is it in, you know, if it doesn't, it's an older motor, you can note that down, because those are places, that's a real plus that you can gain there by having a high efficiency motor. So these are things. Does it have a V-belt drive? Does it have a poly chain, like a timing belt drive on it? Timing belt drives do not slip. Airflow loss through slip is a direct relationship. 10% slip, 10% loss in airflow. It's very important that you don't have V-belts. Nobody, V-belts are really not the way to go. You want to have some kind of timing belt on there. So you want to, those are things that you observe. I talked earlier about measuring all that information, and you have some information from the customer. The other thing is, when you look up into your tubes and you look on a little bit of an angle, you can't look straight up, but if the louvers are open and it's a sunny day, you should be able to see through them. If you can't see through them and the louvers are open, and quite honestly, you know, I say, are the louvers open? They say, yeah, but I actually climb up the stack and I make sure the louvers are open, and you'll see that in the video tomorrow. We got to make sure, because if you assume something, the louvers are closed, you just wasted a whole day of your customers' money, your time, everybody's time, and you haven't, you know, that's part of the test. You got to do it thoroughly. So we want to look in. If there's holes in that fan box, we want to make sure that we correct them. So I think we've pretty much covered everything that we want to talk about here. What I want to do is I want to introduce Mike Norgren, because he's going to be helping us with talking about the fans, but also Mike is very skilled on the vibration analysis part of a fan, and in my fan paper it talks about some of the few things that you look for that can be a little bit of a troubleshooting sort of thing. And so it's been very nice. Thank you very much. And on the bottom of the screen you'll see the email addresses or websites that you can get some of this information. And I'll turn this over to Mike Norgren from Hudson Products.
The vibration part of this exercise is something that I just wanted to focus on lightly here. Because one, without the right equipment up there, the instrumentation, it's going to be hard to really identify what your vibration is. But I wanted to just touch on it in case you notice this while you're up there doing this vibration and airflow testing. Now, one of the things that we want to look at when we're looking at vibration is if by any chance your vibration is at fan speed, you'll notice that you're having a shake up there that is at the same speed of the fan. The first thing that really we want to look for, and it's very important to note this, that on the Hudson fans, you'll see these little holes right here at the tip. And we put those in there so we can actually stop the fan and check these holes to make sure they're not blocked by any debris. You check to make sure they're clean and they're draining out any type of moisture, water. Start your fan back up and see if the vibration's gone. We have asked people to do this via the telephone before we go out to their facility to check their vibration. This has taken care of the problem. So that's pretty common to do that, and go ahead and check that. If you notice the vibration is more like at a blade pass, we call it, that is the fan speed times the number of blades, it's harder to detect without having instrumentation. But what this is the most dominant frequency or vibration that you're going to notice when the fan's running, because it's going over obstacles in the fan and causing a little vibration. But another problem vibration would be at your motor speed. This is where we're looking at drive components that could be a problem, or bearings. So really all we wanted to touch on here lightly was the vibration and the issues that it connects with. Most of your facilities do have people in there that are skilled with vibration, and they can analyze these things, and it's just good for you to know this. I just wanted to make this another key point that I've noticed out in the field, that we do run across vibration issues when we're doing our fan testing. But other than that, that's the only little piece that I wanted to add. I think this information is very important, and really it's a lot easier for us to send this video out to you guys and have you review it rather than us sending out a paper trying to explain to you what we're going to be doing at your facility. Or if you would like, you could test on your own. But Any other questions, please feel free to contact me or Nick Agius, and we'd be glad to take care of it. Thanks a lot. Appreciate this opportunity.